So, hello everyone. In this module, uh, we will be going to discuss about the Thevinin theorem, Thevinin and Norton theorem. We are going to study in this lecture. So, this Thevinin theorem we will study for two type of circuit. One will be having only independent sources, and another when there is a dependent sources. So for both type of sources, their calculations are slightly different. And the books which I will follow for this type of theorem is Basic Electrical Engineering by D.P. Kothari and I.J. Nagrath. And another book that I will follow, Basic Electrical Engineering by Fitzgerald, fifth edition. So these two books I am going to follow in this video. First of all, I will give you the statement of Thevinin theorem. So, what is Thevinin theorem and how can we define it? So, the statement of Thevinin theorem is any linear circuit containing several independent voltage sources and resistances, independent voltage sources or current sources, maybe voltage sources or current sources and resistances can be replaced by just one single voltage source in series with a single resistance current connected across it. In other words, it is possible to simplify any electrical circuit, no matter how complex, to obtain equivalent two-terminal circuit with just a single voltage source in series with resistance or impedance connected to load. So this circuit means any linear circuit. Linear circuit means the circuit which where we can apply, where output is proportional to the input, and where we can apply the superposition theorem. If circuit is linear, we can apply superposition theorem. So this theorem is applied for linear circuit. Also bilateral word will be also used, that is called bilateral. The meaning of bilateral is that, suppose here I am giving the current in this direction and here current is coming outside. So if we change the direction of the current like that, we can also send current from here to here. Means as in the example of resistance, we can send current in this direction. Same resistance, we can also send current in this direction also. Same for capacitor is also there. For inductor also there. We can transfer the current from this side to this side or from this side to this side. In the case of inductor also we can send the current from this side to this side and this side to this side. That is why it is called bilateral element. As in the case of diode, we cannot do this. Means only this is unidirectional element, unidirectional. These are the resistance, capacitance and inductances are bilateral elements. So we can transfer the current from one side to another side and from another side to this side also. That is why it is called bilateral element. So how we can do this work? It is very simple to analyze this circuit. Suppose we have a circuit like this. Suppose we have a circuit containing so many voltage sources, maybe like this. If we have a circuit like this, here current source is also there, voltage source, current source, another resistance, here also voltage source like this, and here it is a, I'm drawing one, here also voltage source and like this here, and this is the load resistance. And we want to find the current in this load resistance using the Thevinin theorem. So how we can analyze this circuit? So to analyze this circuit and to find the current in this resistance, the methods and the steps needed are, I'm going to steps. Step number first is that, okay, we nullify or we nullify the effect of this voltage source and this current source. So step number one is to find RTH. This is called Thevinin resistance. This is called Thevinin resistance. And how we can find this Thevinin resistance? We have just to remove this element where we have to find the current. So by removing this, and the voltage, all independent voltage sources are short circuited and all independent current sources are open circuited. These are the independent voltage and current sources. So all voltage sources are shorted and all current sources are opened at a time, not one by one. As in case of superposition, one by one we are doing, but here at a time we have to short all the voltage source head and all current source we have to open it. Then we have to see the equivalent resistance at this terminal, at the open terminal. So here in this case, what we have to do? This current source is open, this voltage source is shorted, and this voltage source is shorted. This is the resistance, and this voltage source again it is shorted, and this portion is our opened terminal. This here RL is open. Suppose this value, whatever this value is there, suppose if this is R1, R2 and R3, so we have to find here the equivalent resistance at the open terminal, and this resistance is called RTH. We have to consider this is called RTH. So whatever value will be, suppose if I send current here, this current will go here and there is the short circuit path, so it will come here. So here RTH will be simply R1. So it will be R1 will be here the RTH. This is the first task we have to find it. Now another task is, now the second point is, we have to apply all the current and voltage sources, and then we have to find the voltage at the open terminal. Means second part is like this, we have to apply all the voltage and current sources like that I am applying here. I have taken a random example. So here we have to apply all the voltage sources, but keeping this load resistance open, and we have to find here VOC, that is called open circuit voltage, and this open circuit voltage is nothing but it is Thevinin voltage, and this Thevinin voltage is open circuit voltage. So RTH is calculated, VTH is calculated, so we have to draw a circuit like this. Here RTH is this much and VTH is this much. So these two things are connected in series. This is actually called Thevinin equivalent. Thevinin equivalent. This is called Thevinin equivalent. Thevinin equivalent. So this thing is only Thevinin equivalent from here to here. Now we have already opened this RL. So now you have to connect this RL, and this RL will, now current in this circuit we can find very easily the current flowing. That current here I will be equal to how much? This current I will be equal to VTH divided by RTH plus RL. That is very simple to find this current. So using Thevinin theorem, we can find very easily the value of the current flowing in the load resistance. So I have drawn this circuit for independent sources only. For dependent sources, I will also discuss later. But before going to dependent source, I am going to solve some problem related to the Thevinin theorem from the book of I.J. Nagarath and D.P. Kothari. So now I am going to discuss one problem. Problem is, this is a current source having value 1 ampere and 8 ohm. This resistance is 8 ohm. This is 1 ampere. And here 2 ohm resistance. This is 20 ohm, and a voltage source. This is 2 ohm. This is 20 ohm. And this one is plus minus 32 volt. And this one is here a resistance connected is RL. This is RL. Now in question, it is asked to find Thevinin equivalent. In this question, it is asked to find Thevinin and Norton equivalent across AB. You have to find Thevinin and Norton equivalent across AB. So first of all, I would like to find RTH. What is RTH? So how we find? Our step one is, first of all, we have to remove this RL and the effect of this voltage source and the effect of this current source. So now our circuit will be like this. Just removing, and this, it is open circuited here. This portion is like this. This is like this, and this 20 volt will be now short circuited. 32 volt. This is 20 ohm. This is 2 ohm, and this is 8 ohm. And here, this portion RL is removed. This is A and B. Now we have to find the equivalent resistance between A and B. So that A and B equivalent resistance is called Thevinin resistance. So if you see here, the division of current, means some I current is coming here, it will go here I1, and I2 will go here. So this I1 will go here also and coming here, and this I2 also come here, and I1 plus I2 will go here. This is I is nothing but it is I1 plus I2. So the amount of current coming is equal to amount of current leaving. So these two will be in series, and its series equivalent will be in parallel with the 20. So RTH will be simply equal to, this is 10 in parallel with the 20. So two resistances are parallel, so we have to just multiply it and add it to divide. So 30. So it will be equal to how much? It will be equal to 20 by 3 ohm. So RTH is our calculator. RTH is found now. RTH is calculated. So now our next task is to find the VTH, means here open circuit voltage we have to find by connecting all the voltage sources and current sources. So we have to find this value. So here I am drawing again the same circuit. So by connecting all the voltage sources and current sources. So now my circuit is like this. Here it is like this. So it is 20 ohm and plus minus 32 volt, and this one is 2 ohm, and this one is 8 ohm, and this is 1 ampere, and this portion is open circuit. is opened. Okay, so we have to find the voltage at here VOC. This is called open circuit voltage. So the simple way is this: convert this current source into voltage source. So we have to multiply it, and we have to draw this circuit again. So it will be like this. It is like this. So this 1 ohm will come in series, and if you multiply 8 by 1, it will be 8 volt, and positive will be upside because the arrow of current is upside, and negative will be this. And here it is given 32 plus minus 32 volt is given, 20 ohm is given, and this terminal is open terminal. This is A and this is B. It is open. Now see how we can find the voltage at terminal A and B. This one is 2 ohm. You see here a simple one. Closed loop is there like this. Suppose their current flowing is I. So we can write Kirchhoff voltage for this loop, and we can find the value of current. Once we find the value of current, we will very easily able to find the voltage across the AB, that is open circuit voltage. So first, you see this you can also draw the circuit like this. There is one voltage source and all these resistances 1, 2, 20. All these are in series because this current is going only this loop, because there is an open part, so none of the part of I will go here. So 1 plus 2, sorry, not 1, this is 8. 8 plus 2 plus 20 will be 30 ohm, and current I is flowing here. This is 8 volt positive, and here it is 32 volt positive. So the direction of current, if you write like this, I will be equal to 8 minus 32 divided by 30. So it will be equal to 8 minus 32, means it will be 24 minus 24 divided by 30. So it is 8 minus 8, and it is if we 10, so it will be minus 0.8. It means the direction of current is not this, direction of current is along this direction. So the actual current flowing is not anti-clockwise, it is in this direction. It is not in clockwise, it will be in anti-clockwise direction. So what will be the value of I? So I magnitude is 0.8 ampere in anti-clockwise direction. Now we have to find the voltage at A and B. So how we can find it? So many times, many student has confusion how we can find. So I give you one very, very simple idea, that you just draw the circuit like this. 32 volt is there, and this is 20 volt ohm. And now I am drawing. Here we have to find, this is open circuit voltage, and in this element the current flowing is like this, and this value is 0.8 ampere. Current is flowing from this terminal to this terminal. So because of this direction of current, positive will be here and negative will be here, because current always flows from higher potential to lower potential. So sometime keep in mind that this positive is not due to this positive, maybe due to this positive, but not necessary. This positive is due to the direction of flow of this current 0.8 ampere. So positive will be here, negative will be here. So now we have to find the voltage from here to here, A to B. So from A to B, what we have to do? Let us consider a fictitious voltage source like this. I'm considering here a fictitious voltage source. Positive is taken here because we have to find voltage from A to B. So A we have to take positive and B negative. Let its value is Vx. And Vx is nothing but it is VOC or VAB. This fictitious voltage source I had applied here. So in this case, we go for closed loop and apply Kirchhoff voltage law. So start from any place. I am starting from here and going to here. So positive terminal, first we encounter positive terminal. So you write positive Vx. Then I am coming here and I am going here. Then we meet negative first. So you write negative. Irrespective of voltage drop and fall, you forget it. Just whatever you are first meet positive, then write positive. If you meet negative, you just write negative. So I am meeting here negative, I have written it negative. Here I am meeting positive, so we have to write positive. How much voltage? Resistance is 20 and current multiplied by 0.8 equal to 0. So this gives us Vx equal to how much? This 32 will come here and at minus 16, it means 16 volt. So our Vx is 16 volt. So now Vx is calculated and so we can draw the Thevinin circuit. Thevinin equivalent circuit will be like this. RTh is already calculated. How much it was? RTh was 20 by 3 ohm. And this VTh is how much? Just we have calculated 16 volt. This is called VTh, Thevinin voltage. This is called Thevinin equivalent circuit. So our Thevinin equivalent is drawn. So in Thevinin, what we have done? I'm just recapitulate the, we have find RTh and VTh. These two things, once we find, our Thevinin equivalent is completed. This is called Thevinin equivalent. Thevenin's equivalent. But again, I'm telling, I'm applying this rule for only independent sources. When dependent source is there, the rule will be different, which we will see later. So here we have calculated. Suppose here whatever value of resistance that is opened from this terminal. So if the value of resistance is known, let us draw the circuit again. So whatever value of I have resistance opened, so I have just calculated here VTh and RTh is 20 by 3. And this resistance is, this voltage is 16 volt VTh, and whatever resistance we have opened, now we have to connect this RL resistance, load resistance, and then we can very easily find the value of current. Suppose this RL is 5 ohm. I am just taking an example. So I we can find very easily 16 divided by 20 by 3 plus 5. So this ampere current is flowing. And if it is also asked find the power in this resistance, we can also find power in load, that will be equal to I square multiplied by RL. I will be calculated from here and RL is given 5. So we can get the value of this power. So I give you one concept here. If this RL is, suppose if this RL is variable, if I am changing this RL, this load resistance is here, and I calculate the value of RTh is fixed here. RTh, we cannot change here. RTh is in for all the cases. RTh will be same, and we have to calculate TL. Suppose RL I am changing, and this is 20 by 3. Suppose RL I am changing 1 ohm, I am writing. Another place I am writing it as 0 also. RTh will be same, 20 by. And here I am writing 5 ohm and RTh is same. And RTh is same. But here I am writing RL as 20 by 3 and RTh is also 20 by 3. So for all the cases, you just calculate this power. So to calculate this power, what you need to do, first we have to calculate the value of current, I. I will be equal to VTh divided by RTh plus RL. So for different values of load resistances, we can find different value of current and power also. Once we find the value of current, We will also find the power, that is equal to I square into RL, load resistance. Here also I square into RL. Here also I square into RL. So once we calculate, you will see that the value of power for this case will be maximum. Maximum power will be obtained when the load resistance is equal to Thevenin resistance. Only the condition when we get the maximum power. You can calculate this and you can verify this. If the load resistance when becomes 20/3 equal to Thevenin resistance, then power available in the load will be maximum. Now we will see how to calculate the Thevinin. We have solved the problem related to the Thevinin theorem. Now we will see for the same problem how we will find the Norton theorem. Now for the same problem, if we need to find the Norton equivalent. So for Norton equivalent, we will find it by two methods. So one direct method I am giving here. Then another method is also there that we will go from Thevinin theorem to direct Norton theorem. But here I am going to discuss direct Norton theorem. See how we will find the Norton theorem. This is 1 ampere. This resistance is 8 ohm. This one is 2 ohm. This is 20 ohm. This is 32 ohm, 32 volt. And this resistance is RL resistance. So in Thevinin theorem, what we are doing, we are opening it. But in case of Norton theorem, what we are doing, we are just making it short like this. We are doing it short. And RTH, whatever we have calculated using Thevinin theorem, will remain as RTH, whatever we have found, is also equal to Norton resistance, that is called Norton resistance Rn, Norton resistance, which is same, whatever method we have adopted for Thevinin theorem, Norton resistance same. But here in Thevinin it was opened, but in Norton it is shorted. And I am writing here the current flowing is ISC, short circuit current. So once we find this value of the short circuit current, the Norton equivalent is like this. It is like this. This is called ISC, short circuit current. That is nothing but it is called also Norton current. And the resistance, whatever we have calculated for Thevinin, it will be placed here in parallel. That is called RL. And after this is called Norton equivalent. This is called Norton equivalent. Norton equivalent. This is called Norton equivalent. So short circuit current is called Norton current, and this resistance is now placed in parallel with the short circuit current, that is called Rn. Now whatever the load resistance we have, this portion is only Norton equivalent. So whatever resistance we have opened, now we have to apply here it RL, and we can very easily find the value of this RL, current in the RL. Suppose this is IL. So this is the current source and two resistances are connected in parallel. So we know the current division rule very easily. We can find IL will be equal to this current multiplied by this resistance, IN multiplied by RN and divided by Rn plus RN. So using this relation, we will find the value of the load current using the Norton theorem. I will check also Thevinin theorem. We can also go to here directly, whatever Thevinin equivalent circuit we have drawn. But first I check with the Norton theorem. So how we find the short circuit current? Let us see how we can find the short circuit current. That is very simple, not difficult. So you see here, again I am going to transfer this current source into voltage source. So positive will be here, negative will be here, and this 8 ohm resistance will be placed here. This is 2 ohm, this is 20 ohm, and this is a voltage source of 32 volt. And this will be 8 volt, and this is 8 ohm, this is 2 ohm, this is 20 ohm, and it is, the circuit is like this, and here it is ISC, it is short circuited ISC. Okay, so now we will see from here there is a 8 voltage. When it is shorted this portion, what will be voltage here? The voltage will be here, the voltage will be here 0. When it is shorted, current will be maximum, but voltage will be 0. So two voltage sources, this 8 volt source and this 32 volt source, this 32 volt source will give a current that I am writing here, suppose I1, and this current I am writing here as I2. So I1 and I2 is flowing here. So ISC, that is called Norton current also, short circuit current, that will be equal to I1 plus I2. So we have to find the value of I1 and I2. So let us see how you find. This is the 8 volt and here voltage is 0. So potential difference divided by resistance is called current. So I2 will be equal to 8 minus 0 divided by 10. This 8 minus 0 divided by 10 ohm. So this will be 0.8 ampere. And in same way we can also find I1. I1 will be equal to 32 minus 0 divided by 20. Potential difference divided by resistance is called current, Ohm's law. So it will be 1.6 ampere. So ISC, short circuit current, will be equal to, that is also called Norton current, and which is equal to I1 plus I2. That current will be equal to 0.8 plus 1.6, that will be 2.4 ampere. So this value of current is now calculated using the Norton theorem. ISC is 2.4 ampere. So our Norton equivalent circuit will be like this. This current we have to put here, and this Rn is 20 by 3, that is RTH, and here we have calculated it is 2.4, that is called IS, short circuit current, and that is also called IN, Norton current. So by using direct method we have also calculated this value, and if we directly go from Thevinin theorem, then we can also find this equivalent circuit. How we can find? Let us check. So we can directly also calculate the Norton current by using the Thevinin. So what was our Thevinin equivalent? Our Thevinin equivalent was, this was the resistance, that was 20 by 3 ohm, that is RTH. And what was the VTH? VTH was 16 volt. So we can, this is our Thevinin. This is our Thevinin equivalent. Thevinin equivalent. We can directly go from here. This is a voltage source and resistance in series. We can convert it into current source. So current source, how we can convert? So this is current source, and just we put this resistance in parallel. This resistance is 20 by 3 ohm, and by converting this voltage source into current source, we have to divide this voltage by resistance. That is, current is simply voltage by resistance. So here I, this I will be equal to this voltage divided by resistance, 16 by 20 by 3. So 3 will go upside, 8 to ja, no, this you, we have to 4 4 ja, 16, 4 5 ja, and 3 will go 12 by, it will be 12 by 5, means 2.4. So you see this current will be 2.4 ampere. It is same as the Norton equivalent, whatever we have calculated as short circuit. Norton equivalent. So just converting this Thevinin series resistance into parallel and current source, voltage source into current source, we get this Norton. And from Norton to also we can go Thevinin theorem by converting this current source into voltage source. So this multiply by this, we will get this. So directly we can also obtain by obtaining ISC, and if we get the Thevinin theorem, we can also find the Norton equivalent.